Hi there, welcome. This is a quick walkthrough of the production process of the beer shot you just saw. The main focus of this walkthrough will be the simulation process, but materials, lighting and rendering won't be covered in this video. You should have a basic knowledge of the software so that you can follow the tutorial easily. I suggest you check my YouTube channel. In section 02 and 03 you will find introductory tutorials to help you understand and quickly get started in Houdini. Anyway, let's start. Although it's a single shot, it's always advisable to consider the production phases. And here you are: pre-production, production, and post-production. In the pre-production, of course, the idea or a specific brief is the starting point. In this case, it is pouring beer into a glass with foam and bubbles. Then, an important step is to research references and techniques. Real references are the most important ones, but CGI references are also important. Here I have listed the main reference for this project. In this list, maybe you can identify very talented guys such as Peter Höhsl, 9 Between, Danny Barnhart, and Entagma. In the description, you can also find these links. Once the idea or brief is clear and the references have been gathered and studied, it's important to start with a basic layout for the shot and perform initial simulation tests to be sure we have the right techniques for the shot. Now, let's continue with the production process. Obviously, we have to model a glass to pour the beer into. Also, as a detail, we will add static drops on the glass surface. It would be ideal to create simulated drops, but for simplicity, we will model static drops only. The glass will have a simple animation. It will be rotated from 45 degrees to 90 degrees, and the camera will be animated to follow the glass animation. Now, in the simulation process, we will set up the glass as a collider object, and a small sphere will be used as an emitter to pour the beer. This emitter will be animated to follow the glass. With the emitter and the collider, we will set up the fluid simulation. In this simulation, the most relevant point is that we will have to set up different densities to be able to differentiate the liquid from the bubbles and foam. All the points from the simulation will be used to generate the mesh to form the liquid surface, while the lower density points will be used to form the bubbles and foam. As an additional detail, extra bubbles will be emitted from the bottom of the glass, but this last task will be an assignment for you to do. With all the elements in place, we will start creating and assigning materials to each element, but all the materials will be of the refractive type. The glass and beer will be completely transparent, the glass will be without color, and the beer will have an orange color. Bubbles will be less transparent and rough, while the foam will be much less transparent, rougher, and white in color. For the lighting, a couple of area lights will be enough, and also an HDRI light to get some reflections on the glass and liquid. As stated before, materials, lighting, and rendering won't be covered in this walkthrough. Now, let me quickly show you the schedule for the tasks. As you can see in the Gantt diagram, the pre-production took a couple of days. In the production, of course, the main task was the simulation, and it took 4 days. And lighting and rendering took a couple of days. Okay, that was a quick high-level walkthrough of all the processes. Now, let's go to Houdini to review the nodes in the network. Here in Houdini, we have the beer project. The entire network is in one single geometry node named FXBeer in green color. The nodes in blue are just references from the main network, just for the purpose of rendering. Besides, we have a camera in black and the lights in yellow. So, let's dive into the main network. Here you are: modeling, simulation, meshing, foam, and bubbles. Let's start with the modeling, which is pretty basic, just a revolved curve to form the glass, and scattered points converted to volumes to get the drop shapes on the surface of the glass. So, with the curve node, you can draw the profile for the glass. Then, a convert node is used to turn the nerve curve into polygons. Not necessary for this project, but you can place an UV texture node to assign UVs to the curve. Now, a revolve node turns the profile curve into a solid object. And finally, I used a transform node to slightly increase the size of the glass. And we have our static glass model. The animation is also quite simple. With a transform node, I just animate the rotation of the z-axis. That's all for the glass. We have our animated glass. As usual in Houdini, it is important to place a null to identify and reference this point when needed in the network. To render the glass, I add a subdivide node and a pick node to slightly move the surface of the glass to have better interaction with the liquid. Then add normals and assign a material. And the glass is ready for rendering. For the static drops on the glass, I used a technique from Entagma. To them, the merit of this technique. So, I'm going to go quickly on this. If you want to see this process in detail, I put the Entagma tutorial link in the description. So, we start with the animated glass. Here I also subdivided the surface and then picked at a small distance. I used a transform node to scale by 3 the size of the glass, but later I realized it was not necessary. Anyway, let's continue. So we have our animated glass, but to place the drops, it's easier if the geometry is static and in a vertical position. To achieve this, I place a time shift node to freeze the animation on the last frame in which the glass is vertical. Now, this is the Entagma technique. In one stream, with blast nodes, they isolate the exterior glass surface and then add normals, not to the vertex, but to the points. Then, a scatter node to scatter points on the surface. Then, in an attribute bob node, Entagma uses a noise, fit ranges, and a ramp parameter to get variation and export this to the p-scale parameter using a bind export node. Then, in one stream, the drops are slightly scaled, and in the other stream, they are also scaled. But the right stream is also moved upward with this attribute bob. Entagma uses the cross product to define directions and the p-scale to define the amount of movement. Please visit the Entagma tutorial to get a full explanation of this technique. Now both streams are merged. And with the Copy to Points node, a sphere is copied onto the points to have real geometry. Then, with a BDB from Polygons node, we get a BDB volume. And using a BDB combine node, we subtract the glass BDB volume from the drops volume to avoid intersections. Then a BDB reshape SDF node to expand the volume. And a BDB smooth SDF node to soften the volume. And finally, a convert BDB node to turn the BDB into polygons. At the end, another attribute Bob moves the surface inward to get proper interaction between the drops and the glass. Here, Entagma uses the XYZ distance and print UV functions to achieve this effect. Once again, please visit the Entagma tutorial for a detailed explanation. Now we have the drops on the static glass. But to transfer the glass animation to the drops, we need a point deform node. In the first port, connect the static drops. In the second port, connect the static glass. And in the third port, connect the animated glass. Now, as you can see, we have the drops following the glass animation. If you remember, I needlessly scaled the glass 3 times, so to restore the original size, I just copied the transfer node with the same parameters, but in this copy, I activated the Invert Transformation checkbox. Finally, I added normals, assigned a material, and the drops are ready to be rendered. Let's go now to the simulation section. To start, we need a collider and an emitter. For the collider, we start from the animated glass. Then we just need a collision source node to get both the polygons and the BDB volume to be used inside the solver as a collider. For the emitter, we need a small sphere to emit the fluid. I placed a transform node to animate the sphere to be in sync with the glass. And an additional transform node to animate the scale of the sphere and add a wiggle movement to get a more interesting emission. Then, I placed a flip-top source node to convert the geometry into a flip source. In this node, I added a slight velocity in the negative y direction. Also, to get a more interesting emission, I placed an attribute noise node to add some variation to the velocity. Now, let's dive into the simulation. For this technique, I have to give credit to Barnhart from Gnomon and his tutorial about flip fluids. For further explanation, please visit the link in the description. This simulation contains the common elements of any flip simulation: flip solver, flip object, emitter, collider, and gravity. Additionally, some nodes are used to manipulate the fluid properties in the simulation. The collider is a static object node, and it's linked to the collider we set up earlier. It's important to activate the checkbox "Use the forming geometry" to take into account the animation. In the flip object, it's important to add the viscosity attribute and the divergence field. At the moment, in the Guides tab, the visualization is based on the viscosity. In the emitter, the subpath is linked to the emitter we set up earlier. Now, in the flip solver, you have to adjust the following parameters. Increase the substeps to get a more stable simulation. In the Particle Motion tab, first in the Behavior tab, activate the Add ID attribute and H Particles checkboxes. In the Vorticity tab, activate Add Vorticity. Now, in the Volume Motion tab, first in the Viscosity tab, activate Enable Viscosity, Viscosity by Attribute, and Slip on Collision. In the Density tab, activate the Density by Attribute checkbox. And finally, in the Divergence tab, activate the Divergence by Attribute checkbox. Now the nodes for fluid processing. This is the Barnhart technique with some adjustments. First, a pop group node to select some points based on percentage and age. These selected points will be part of a group named foam. Then, a pop wrangle node sets the main fluid attributes: density, viscosity, and divergence, based on the age and frame number. The foam group is set with a lower density so that it can float. Next, another pop wrangle to reduce the velocity, also based on age and frame number. Then a pop force node based on the Y position of the particles, pushes the particles from the bottom of the glass. And finally, a pop drag node to damp the particle movement, especially at the end of the simulation. At the end, we have a gravity node with the default parameters. Once the simulation has been set up and adjusted to get the desired results, it's time to cache to disk. First, we need a DOP-I node linked to our DOP network sim and configured to flip fluid. Then, a fluid compress node is used to compact the data to save space on the disk, and a file cache node to save the data on the disk. To see the uncompressed data, you can use an unpack node. I have prepared 3 flipbooks to evaluate the simulation. One using the vorticity attribute. The next one using the density attribute. And this one using the viscosity attribute. Now, to start the liquid, the foam, and the bubbles processing, we need to split into 2 streams. For this, we use a split node and use the foam group created in the simulation. In the first output port, we have the foam. And in the second output port, we have the liquid. Let's start with the liquid. First, we have a particle fluid surface node, which converts our points into a VDB surface. But, as you can see, we get a lumpy surface. It will cause problems with the glass surface. So, we convert the glass into a VDB surface and then subtract it from the VDB liquid using a VDB combine node. Now we have a smooth surface. After that, a VDB smooth SDF node is used to get an even smoother surface. Then, a VDB convert node to turn the VDB into polygons, and an attribute transfer node to transfer the fluid attributes from the points to the polygons. Now we can use a file cache node to save the mesh data to disk. To render this mesh, the usual process. A normal node to add point normals. An attribute blur node to blur the normal to get an even smoother surface. An attribute promote node to restore the normals from point to vertex. An attribute delete node to keep the attributes we may need for rendering. An attribute wrangle node to reduce the velocity to avoid excessive motion blur. And a material node to assign a refractive material. That's all for the liquid. Now, let's go to the foam and bubbles. We start from the foam points. With a color node, we set the point's color to white. Now, on this side, we have the glass surface in black. So, we can use an attribute transfer node to transfer the black color from the glass to the foam points within a certain distance. Now, to isolate the top surface of the foam, I was having trouble. So, I ended up doing a quick manual tracking of the foam surface. For this, I create a point and use a transform node to manually track the surface position of the foam, adding keyframes. For what I need, I think the result was enough. Next, using an attribute wrangle, I can read the top Y position of the phone and define a lower and upper range. Now, if the color of the points is white and their Y position is outside the lower and upper range, then it means those are interior points, and we can group them into a group named small. For the big phone, those points are not needed and we'll be deleting them. For the small phone, we do keep all the points. Okay, but there is still an issue. We have points over the surface of the phone that should not be found, so we need to delete them. For this, the manual Y position of the phone surface is useful, but if I set the Y position, add an offset, and delete the top points, it's okay, although I will get a straight line cut. To avoid this new issue, I use a point bob node. Inside this node, I read the manual tracked Y position, add a small vertical offset, and compare with the Y position of the points, but adding a small amount of noise to get a less straight cut. Finally, we add the result to the color output. And if we go outside, we can see in white the selected points that we want to delete. Add a blast node with a color value expression, and it's done. Now, for the small phone, in the left stream, we will process all the phone points. For the big phone, in the right stream, we will start deleting the small point group. Let's start with the big phone. First, using an attribute wrangle, reduce the number of points, let's say to 3%. Then, with an attribute randomize node, let's add variation to the p-scale. Now, to mesh the points, a VDB from particles node is used to turn the points into a VDB. Then, a VDB combine node to subtract the glass converted into a VDB. Then, a VDB smooth SDF and a VDB convert node to turn the VDB into polygons. As usual, an attribute transfer node is used to transfer the fluid attributes from the points to the polygons. And finally, a file cache node to save the mesh data to disk. To render the big phone mesh, we use a similar procedure to that for the liquid. A normal node to add point normals, an attribute blur node to blur the normals to get an even smoother surface, an attribute promote node to restore the normals from point to vertex, an attribute delete node to keep the attributes we may need for rendering, an attribute wrangle node to reduce the velocity to avoid excessive motion blur, and a material node to assign a refractive material. That's all for the big phone. Now let's go to the small phone. Let's start with an attribute randomize node to add variation to the p-scale. Of course, the scale value for the small foam is smaller than the scale used for the big foam. Now, to avoid issues of bubbles going inside the glass, I used an attribute transfer node to get the normals from the glass. Then a pick node to push inside the points a very small distance. Then I used a group node to select the points that are inside the big foam and deleted those points with a blast node. Next, a file cache node to save to disk the points. Since there are quite a few points, instead of converting them to a mesh, it's better to render them as points using primitive spheres during the render process. So we just need to add the following nodes. An attribute delete node to keep the attributes we may need for rendering. An attribute wrangle node to reduce the velocity to avoid excessive motion blur. And a material node to assign a refractive material. That's all for the small foam. Now, extra bubbles in the beer are a nice-to-have element to improve the shot. This is going to be an assignment for you. But I'm going to give you the guidelines to achieve this effect. The idea is to emit extra bubbles from the bottom of the glass and keep these bubbles inside the liquid. To emit bubbles, you can isolate polygons at the bottom of the glass, scatter some points, add a pop network to generate the points. In the pop network, you can add a slight velocity in the y direction and a pop force with some noise to have a nice movement. You could also add a pop advect by volume node to read the velocity from the main simulation and get an even better movement for the bubbles. To keep the bubbles inside the fluid, you can use the same procedure we used for the main bubbles, which was to use the liquid mesh geometry as a boundary and a group node to select the points inside this boundary, and then delete the outside points. Okay, we have covered all the processes for the production phase, except materials, lighting, and rendering. But anyway, to end this video, let's check some guidelines for materials. I think these guidelines may be more useful than a notes walkthrough. For the glass, a standard refractive material is more than enough, no tweaking needed, unless you want to increase the roughness of the material to get a strong frost effect, or introduce procedural or map scratches on the surface. For the bubbles, you also need a standard refractive material, but it's better if you treat it as a thin wall material and not as a solid object. It's also important to add some diffuse to the material. For the foam, you can use a more diffuse material with some specularity and much less transparency than the bubbles inside the water. Here is an important issue. The bubbles, while inside the fluid, should use the refractive thin wall material, but when they are in a range on the surface, they should use the foam diffuse material. So, how do we solve this issue? Well, in any render engine you can mix materials, and that solves the problem, right? Yes, but how to control the mix of the materials? Well, you can use attributes from the simulation such as vorticity, density, and viscosity. Let's check the simulation flipbooks again to realize how useful these parameters are for the shading process. In Houdini, you can read parameters and use them in the shader, but if you are going to export the meshes and points to another software, then don't forget to include these parameters when exporting the Alembic files. Okay, that's all. Thank you for your attention, and I hope this walkthrough will be useful for you in the path of learning Houdini.